On the 3rd of September 1939, Prime Minister Neville Chamberlain informed the House of Commons that Britain was at war with Germany. The Royal Air Force possessed 1,911 aircraft. The Luftwaffe fielded approximately 4,300. But the numerical disadvantage was only the beginning. Britain's aircraft industry consumed roughly 60,000 tons of aluminium annually. Germany controlled nearly every source. The Vereinigte Aluminiumwerke commanded 40% of European production. The Norwegian facilities at Glomfjord, now within reach of German occupation, supplied another 25%. Swiss refineries operated under German influence. French smelters would fall within months. The mathematics was brutal. Britain needed to triple aircraft production within 18 months, whilst losing access to the primary material required to build them. The problem wasn't simply shortage. Britain possessed bauxite deposits in British Guiana, but refining aluminium required massive electrical power. Each ton demanded 15,000 kilowatt-hours. Britain's hydroelectric capacity was negligible compared to Norway's waterfalls or Germany's industrial grid. The alternative was coal-fired generation at triple the cost. Even if power materialized, building smelters required 3 years minimum. The Air Ministry's projections showed catastrophe. Demand for 180,000 tons by 1941. Domestic capacity of 24,000 tons. Every Hurricane, every Spitfire, every Lancaster required aluminium alloys for airframes, engine blocks, propeller blades. The Germans had spent a decade stockpiling. Britain had spent a decade buying from Germany. Into this crisis stepped an innovation nobody had connected to aircraft. Geoffrey de Havilland was born in 1882 in Buckinghamshire, son of a curate. He trained as a mechanical engineer at the Crystal Palace Engineering School, then found work designing buses for the Omnibus Company. Engines fascinated him more than chassis. In 1908, he used his grandfather's inheritance to build his first aircraft in a workshop behind his flat. The machine lasted 4 flights before crashing. De Havilland walked away with minor injuries and complete certainty about his future. If he couldn't afford metal, perhaps he could perfect wood. The aviation establishment dismissed wood as primitive. Metal represented modernity, strength, the future. De Havilland saw mathematics differently. Aluminium's strength-to-weight ratio was excellent, but wood offered advantages the metal enthusiasts ignored. Spruce possessed remarkable specific strength when properly selected and oriented. Birch plywood, laminated with modern adhesives under heat and pressure, created structures stronger than equivalent aluminium frames whilst weighing less. The problem was manufacturing complexity. Metal could be stamped, riveted, welded by semi-skilled labor. Wooden aircraft construction required cabinet-making expertise, careful moisture control, precise adhesive curing, grain orientation knowledge accumulated over years. De Havilland spent the Great War building aircraft for the Royal Flying Corps, then founded his own company in 1920 at Stag Lane Aerodrome. His DH-60 Moth trainer used wooden construction throughout. The Air Ministry ordered metal. De Havilland persisted with wood, refining techniques, developing new adhesives, training craftsmen. By 1925, moths were setting records. By 1928, they dominated civilian aviation training worldwide. Amy Johnson flew one to Australia. Francis Chichester flew one to Japan. The Air Ministry still preferred metal for combat aircraft, but de Havilland's company had solved problems nobody else considered. How to laminate compound curves, how to achieve consistent joints between dissimilar woods, how to protect structures from tropical humidity and Arctic cold. The company expanded through the 1930s, producing metal aircraft to Air Ministry specifications, whilst continuing wooden innovations in civilian machines. The DH-88 Comet Racer won the 1934 McRobertson Air Race from England to Australia, constructed entirely of wood and averaging 160 miles per hour over 11,300 miles. The fuselage was birch plywood, shaped using a technique de Havilland patented, laminating thin veneers over a male mold with casein adhesive, creating a monocoque shell lighter and stronger than aluminium semi-monocoque construction. Traditional fabric-covered wooden frames were obsolete. De Havilland's molded plywood was revolutionary. But the Air Ministry wanted metal bombers, metal fighters, metal everything. Then the war started, and the metal disappeared. In November 1939, the Air Ministry issued Specification B-1/39 for a high-speed unarmed bomber relying on speed rather than defensive armament. The specification demanded 400 miles per hour at 30,000 feet, carrying 1,000 pounds of bombs to Berlin. No existing bomber approached these figures. The specification also demanded aluminium construction. De Havilland submitted a wooden design. The Air Ministry rejected it immediately. De Havilland resubmitted. The Ministry rejected again. Metal was modern, wood was archaic. The decision was final. De Havilland asked one question: where would the aluminium come from? The Ministry had no answer. In January 1940, de Havilland received permission to build a wooden prototype using company funds, no government contract, no guarantee of orders. The transformation required was extraordinary. De Havilland's workshops at Hatfield had produced perhaps 200 small wooden components daily for civilian aircraft. The bomber would require 35,000 components. Each wing half contained 9,400 pieces of wood, cut to tolerances of 5/1000ths of an inch. The fuselage shell comprised 1,280 separate veneer sections. Scaling production meant training thousands of workers in techniques that had taken de Havilland's craftsmen years to master. The company hired furniture makers from High Wycombe, piano builders from London, boat builders from Southampton. By March 1940, employment had increased from 1,800 to 4,200. By September, 8,900. By June 1941, 14,200 workers, 67% of them women with no previous woodworking experience. The construction technique was unlike anything in aircraft production. The fuselage comprised 2 shells, each built over a concrete mold. Workers laid birch veneer strips diagonally, alternating grain direction, brushing each layer with casein adhesive heated to exactly 65 degrees Celsius. Too cold and the glue wouldn't cure properly. Too hot and it would set before spreading evenly. 7 layers of veneer, each 1.5 millimeters thick, built up the shell. Then the assembly went into an autoclave at 90 degrees Celsius under 100 pounds per square inch pressure for 6 hours. The shells emerged as single-piece monocoques requiring no internal framework. The 2 halves were joined with more adhesive and bolts, creating a fuselage stronger than aluminium construction whilst weighing 800 pounds less. The wings used a different approach. Spruce spars ran the length, shaped from carefully selected timber, with grain running perfectly straight. Birch plywood ribs, cut on power saws by women who had been secretaries and shop assistants 6 months earlier, were spaced every 12 inches. The upper and lower surfaces were birch plywood stressed skin, glued and screwed to the internal structure. No fabric covering, no dope, no external bracing. The entire wing was a load-bearing structure, with every component contributing to strength. An aluminium wing of equivalent strength would have weighed 340 pounds more and required 18,000 rivets that each created a potential stress concentration point. The wooden wing had 0 rivets. Training the workforce was relentless. Instructors demonstrated how to read wood grain, how to detect compression failures invisible to untrained eyes, how to mix adhesive to perfect consistency, how to recognize proper curing. Women who had never held tools beyond kitchen knives learned to operate band saws, drill presses, pneumatic sanders. The work was exhausting. The factory operated 3 shifts. Temperature and humidity had to be controlled constantly, because wood dimensions changed with moisture content. Summer heat required constant ventilation. Winter cold demanded heating whilst maintaining humidity levels. The adhesive curing schedule was inflexible, requiring night shifts to remove components from autoclaves at 2 a.m. Dorothy Summers, aged 24, had been a hairdresser in St. Albans. In August 1941, she was gluing wing ribs in Bay 7. She recalled years later. Mr. de Havilland came through one morning and stopped at my bench. He picked up a rib I'd just finished, examined the joints, set it down. He said, "This will keep a pilot alive over Germany tonight." We knew what we were building wasn't practice. The prototype flew on the 25th of November, 1940. Test pilot Geoffrey de Havilland, Jr. pushed the aircraft to 392 miles per hour in level flight, faster than any RAF fighter then in service. Climb rate exceeded all specifications. Range with full bomb load was 1,500 miles. The Air Ministry ordered 150 aircraft in January 1941, then increased the order to 450 in March. The aircraft received designation Mosquito. Production targets were savage: 30 aircraft per month by September 1941, 60 per month by January 1942, 100 per month by June 1942. These numbers would have been challenging for conventional metal construction. For wooden aircraft requiring hand-fitting and curing time, they seemed impossible. De Havilland subcontracted fuselage production to furniture manufacturers. Waring and Gillow, who had built cabinets for ocean liners, now built bomber fuselages. Standard furniture companies in London contributed wing sections. A piano manufacturer in Yorkshire produced tailplanes. The challenge was maintaining quality whilst scaling. Each subcontractor had to install autoclaves, train workers, establish quality control. Government inspectors rejected entire batches for adhesive voids, grain defects, improper curing. In April 1941, production reached 12 aircraft. May showed 15. June managed 18. The target was 30. The pressure was unrelenting. July brought 24 aircraft. August delivered 29th September, achieved 33rd. The growth wasn't smooth expansion, it was controlled chaos. Spruce supplies from Canada were disrupted by U-boat attacks. Birch plywood from Scotland arrived warped from improper storage. Adhesive manufacturers couldn't increase production fast enough. De Havilland's purchasing department scoured Britain for woodworking machinery, buying out furniture factories and shipping entire workshops to Hatfield. Workers were recruited from anywhere with woodworking skills: organ builders, coffin makers, violin makers. The factory operated 24 hours daily. January 1942 produced 47 Mosquitoes. March delivered 68. June achieved 94. The Royal Air Force began combat operations in May 1941. The initial missions were high-speed photographic reconnaissance over Germany. Squadron leader Rupert Clark flew Mosquito W4055 on September 17, 1941, photographing Bordeaux harbour from 25,000 feet. Luftwaffe fighters scrambled. Clark pushed the throttles forward and climbed. The Bf-109s couldn't catch him. He returned with perfect photographs and no damage. The wooden aircraft that the Air Ministry had initially rejected was now the only British bomber that could reach Germany in daylight and return. Bomber Command received the first dedicated bomber variant in November 1941. The Mosquito B Mark IV carried 2,000 pounds internally, plus wing racks for additional bombs. On 31st May 1942, Mosquitoes participated in the 1,000-bomber raid on Cologne. 4 Mosquitoes led the stream, marking targets with incendiaries. They arrived first, dropped accurately, and departed before the main force appeared. Not one was damaged. Of the 1,046 bombers participating, 43 were lost. The Mosquito's loss rate was 0. The military qualification test that proved the design's superiority came in December 1942. The Air Ministry specified that any bomber variant must complete a 100-hour endurance test, including 50 simulated missions with maximum power climbs, combat maneuvers, and full throttle level flight. Temperature cycling from -40 degrees Celsius to +50 degrees Celsius. Vibration testing equivalent to 500 flight hours. And structural loading to 150% of maximum design limits. The test was designed to break aircraft. It broke most. The short Stirling bomber failed at 67 hours with wing spar cracks. The Handley Page Halifax completed the test, but required replacement of 18 primary structural components. The Avro Lancaster passed with minor repairs. The Mosquito B Mark IV completed 100 hours, was disassembled, inspected, and cleared for another 100 hours with no component replacement required. Inspectors found no adhesive joint failures, no delamination, no compression damage. The wooden structure showed less fatigue than aluminium airframes. The results weren't close. In January 1943, the Air Ministry awarded de Havilland a contract for 1,200 additional aircraft at £12,400 each, delivery schedule 50 per month minimum. This was half the cost of a Lancaster bomber. Production scaling continued. February 1943 delivered 87 Mosquitoes. May produced 125. August achieved 163. The workforce had grown to 22,000 by mid-1943. The factory complex at Hatfield covered 2.4 million square feet. Subcontractors were producing components from Scotland to Cornwall. Monthly wood consumption reached 6,500 cubic meters of spruce and 4,200 cubic meters of birch. In combat, the Mosquito's performance was devastating to German defenses. Wing Commander John Wooldridge led a precision raid on the Gestapo headquarters in Copenhagen on 31 October 1943. 6 Mosquitoes, flying at 50 feet over the North Sea, reached the target undetected. They dropped 11 500-pound bombs through the building's windows at precisely 11:14 a.m. The building collapsed. Wooldridge's aircraft was damaged by debris from the explosion, not German fire. All 6 Mosquitoes returned to Britain. Maintenance logs showed the wooden construction's superiority in operational conditions. Before the Mosquito, Bomber Command's average aircraft availability rate was 62%. Aircraft spent 38% of time undergoing maintenance, primarily repairing stressed skin damage, replacing rivets weakened by vibration, fixing cracks around fastener holes. The Mosquito's availability rate was 89%. The wooden structure didn't suffer metal fatigue. There were no rivets to work loose. Battle damage was easier to repair because wood could be carved to fit, glued and sanded smooth, whilst aluminium required metal shops and skilled sheet metal workers. Squadron leader James McLaughlin commanded 139 squadron flying Mosquitoes from RAF Upwood. His maintenance officer reported in March 1944 that the squadron's 16 aircraft had flown 1,247 sorties with 0 losses from structural failure. 2 aircraft were lost to flak, 1 to a fighter, but the remaining 13 aircraft that had absorbed combat damage were repaired and returned to service within days. McLaughlin noted, "The kites took punishment that would have written off metal aircraft. We had one return with a hole through the fuselage you could crawl through. The structural integrity was unaffected because the stressed skin distributed loads. We patched it with plywood and glue. It flew the next night." German intelligence was baffled, then alarmed. Luftwaffe interrogators questioned captured Mosquito crew members extensively about the wooden construction. Documents captured after the war revealed the German assessment. A Luftwaffe technical intelligence report dated August 15, 1943 stated, "The enemy has achieved with wood what we attempted with aluminium and failed to match. The performance characteristics exceed our best fighters at altitude. The manufacturing approach bypasses materials, shortages we cannot solve. Our response capability is limited." The German predicament was strategic. They had spent the 1930s developing aluminium production and all-metal aircraft construction. Their engineering expertise, their manufacturing base, their training programs, everything was optimized for metal. Wooden aircraft construction required different skills, different facilities, different supply chains. German furniture manufacturers had been converted to war production, making other items. Skilled woodworkers had been conscripted into the Wehrmacht. The adhesives de Havilland had perfected required chemical precursors Germany was using for synthetic fuel production. The window for catching up had closed before the Germans realized a window existed. Germany attempted wooden aircraft development anyway. The Focke-Wulf Tar 154 was designed as a direct Mosquito competitor. The prototype flew in July 1943 and showed promising performance. Production began in June 1944. Within weeks, aircraft began disintegrating in flight. The cause was adhesive failure. The specified adhesive used the same chemical base as de Havilland's formula, but German chemists hadn't understood the curing requirements. The replacement adhesive came from a supplier whose factory was destroyed by Allied bombing in September 1944. Production stopped after 50 aircraft were built. None saw combat. De Havilland had been perfecting wood-to-wood adhesion since 1925. The Germans started in 1943 and ran out of time. The strategic bombing campaign added grim irony to the story. RAF Bomber Command and the American 8th Air Force devoted enormous resources to destroying German aircraft production. The Schweinfurt raids in August and October 1943 targeted ball-bearing factories. 590 bombers participated. 120 were lost. German ball-bearing production declined 38% temporarily, then recovered as dispersed facilities came online. The attacks on German aircraft assembly plants throughout 1944 employed thousands of bombers. Hundreds were lost. German aircraft production actually increased in early 1944 through dispersal and underground factories. Whilst these massive raids proceeded at terrible cost, Britain was producing an aircraft that required no aluminium, no strategic materials Germany might have stockpiled, no complex machine tools the bombing was targeting. The Mosquito was built from trees, glue, and craftsmanship. German bombing had destroyed de Havilland's factory at Hatfield in October 1940, killing 21 workers. Production moved to dispersed facilities and continued. By 1944, Mosquito production exceeded 300 per month from factories scattered across Britain. Bombing them would have required finding dozens of furniture workshops and timber yards. The Luftwaffe lacked the capability. The numbers tell the complete story. From 1940 to 1945, Britain produced 7,781 Mosquitoes, consuming 0 aluminium allocated for other aircraft. Each Mosquito required 24 cubic meters of wood versus 2.3 tons of aluminium for an equivalent metal aircraft. The total aluminium saved was 17,895 tons, enough for approximately 1,200 additional Spitfires. The Mosquito's operational loss rate was 1.8% compared to 4.6% for Lancaster bombers and 8.2% for American B-17S flying daylight missions. No Mosquito was ever lost to structural failure in combat. The wooden aircraft that experts dismissed as primitive proved more survivable than metal. The cost differential was equally dramatic. A Mosquito cost £12,400 to manufacture. A Lancaster cost £58,000. A B-17 cost $238,000 American dollars, approximately £60,000 at wartime exchange rates. The Mosquito carried less bomb load than heavy bombers, but could make multiple sorties whilst the heavy bombers underwent maintenance. Operational analysis showed that Mosquito squadrons delivered more ordnance per aircraft per month than Lancaster squadrons, whilst suffering 1/3 the losses. Geoffrey de Havilland's son, also Geoffrey, was killed testing a prototype jet aircraft in September 1946. The elder de Havilland continued developing aircraft until his death in 1965. The company he founded built Britain's first jet airliner, the Comet, and produced military aircraft through the 1960s. The de Havilland Company was eventually absorbed by Hawker Siddeley, which became part of British Aerospace, which merged into BAE Systems. The Mosquito was the last truly wooden combat aircraft. Jets and aluminium proved the future. But for 5 years, wood was superior. The legacy extends beyond aircraft. Modern composite materials used in contemporary aircraft descend directly from de Havilland's molded plywood techniques. The principle of laminating materials with different properties to create structures stronger than equivalent solid construction was revolutionary in 1940. Today's carbon fiber composites use the same approach. Fibers oriented for strength, resin providing cohesion, layers built up over molds, cured under heat and pressure. The Boeing 787 Dreamliner is 50% carbon composite by weight. The Airbus A350 is 53% composite. Both trace technical lineage to the wooden shells de Havilland developed when aluminium disappeared. The strategic reversal was complete. In 1939, Germany controlled European aluminium production and dominated aircraft technology. Britain faced material starvation and technical disadvantage. By 1945, Britain had produced thousands of aircraft using materials Germany couldn't access, using techniques German industry couldn't replicate, achieving performance German engineering couldn't match. The Mosquito flew higher, faster and farther than any German bomber whilst being cheaper, easier to build and more survivable. German engineers, who had dismissed wood as primitive in 1939, spent 1944 trying desperately to copy techniques a British engineer had perfected in peacetime building sport aircraft. The global production of wooden combat aircraft ended with the Mosquito. No nation attempted similar construction after 1945. The technology worked perfectly, but the world had moved to jets and aluminium and eventually composites. Yet the Mosquito demonstrated something profound about innovation and crisis. The solution to Britain's aluminium shortage wasn't finding more aluminium. The solution was a different approach nobody had considered seriously, developed by someone the establishment had dismissed, using materials that seemed archaic, employing techniques that appeared impossibly complex for mass production. The Air Ministry wanted metal aircraft. De Havilland gave them wooden aircraft that outperformed everything metal construction could achieve. The mathematical advantage held by German industry in 1939 was reversed completely by 1945. German engineering came in second place.